This is how to calculate G-force on a swing. First, I'm going to do those circular swings that you see at amusement parks, where the swing looks like a giant table, like a pedestal table with a single post that runs up the middle. And then on the edge of that table, you have these chains that hang down, and then there's these seats on the end of those chains. So the whole tabletop starts spinning around, and the people in those swings will swing out. This is how to calculate the G-force on those people. It's super easy. After I do this type of swing, then I'll just do a basic playground swing. This is so easy, a kid could do this if they knew basic SOHCAHTOA. So a kid could watch my video on SOHCAHTOA, basic trig, and learn basic SOHCAHTOA and then solve this really quick. Okay, so here we have our tabletop pedestal right here. And we have G as the force of gravity pulling down, 9.8 meters per second squared. The force pushing out there or pulling out is V squared over R. That's your centripetal acceleration. So it's being accelerated in actually by the centripetal force of V squared over R. Then you have your centrifugal force as the counterforce. And then you have A here, which is just the acceleration that these people feel. And A will be the G-force that they feel. Whether you have this tabletop here spinning around and centripetal force swinging these people out, or whether you just have a rope or a cable attached to this weight right here and you're pulling this weight directly out, the math is still the same. The easy way to do this is just to understand that the G always pulling down there, the force of gravity is always 9.8 meters per second squared. So since this line right here always equals 9.8 meters per second squared, that will be the adjacent to the angle or the adjacent leg. The other legs of this triangle will just be some ratio of that G. So for example, you could have this swing going around really fast and these people swung way out there. So the G vector for gravity, which is 9.8, is going to be very small relative to the other legs of the triangle. So that means these other legs are going to be very large. And these people will experience a large G-force because G-force is determined by the length of this vector or this cable right here on which the people are attached and they're swinging around. All right, so here's what I did wrong the first time I made this video. Actually, it was the right way to do it, but it was just a really long, complicated way. You don't need V squared over R, which means you don't need this leg of the triangle right here. You don't need the opposite leg. We already know theta, or we can measure theta, and I'll show how, and we'll know G is 9.8. That's all we need to calculate G-force. When I first posted this video, I ended up taking it down because it was just a long, complicated way to solve it. But when I first made this video, I was trying to guess the length of the chain right here by comparing the height of the people sitting in the chairs. And I was trying to guess how wide this tabletop was right here. And then I would try to determine the velocity that these people were swinging around. And that's just a long, complicated way to do it, so we don't have to do it that way. Also, when I was trying to figure this out, I was trying to decide how the width of that tabletop or the radius of that tabletop mattered, or if it mattered. It turns out I don't think it does. I think we can ignore the radius of this tabletop and just pretend that this cable goes all the way up to a central post. And I was also wondering if I should measure the angle theta as this angle right here from the mast to the edge of the tabletop, or should I measure the angle from the mast all the way to the center post, right here where the tabletop meets the center post. It looks like this is the way to do it. Just measure the angle from the edge of the tabletop down to the mast. Okay, so we have cos theta equals adjacent over height. That's G over height. G is 9.8. What I did for this, I just watched a video on YouTube of some people at an amusement park going around one of these swings. I paused the video and I measured with just a ruler, and it was, I think it was approximately 2 centimeters going down and 2 centimeters going over, which made it a 45-degree angle. I just caught my first error here. This is not arc cos, this is arc tangent. So it's 2 divided by 2. Take the arc tan of 2 divided by 2, which is the same thing as arc tan of 1, equals your angle, which is 45 degrees. Cos 45 equals 9.8 divided by height. So it's G divided by the acceleration there. You're going to get 13.9. 13.9 meters per second squared for the acceleration. Divide that by the acceleration from gravity here on Earth, 9.8 meters per second squared. You get 1.4 Gs. So they are experiencing a 1.4 G force. Now we can calculate within just a few seconds what that angle theta will be, depending on how many Gs or how much G force these people are experiencing. The arc cos will equal G over 4 times G, so that's adjacent over hypotenuse. Adjacent is G, which is 9.8. The hypotenuse will be 4 times that, so it'll be 4G. We take the arc cos of G divided by 4G. G divided by G cancels. We're left with 1/4. So we have arc cos of 1/4 equals the angle theta. That's 75.5 degrees. And you can easily do the same for 10 Gs of force. That'll just be the arc cos of 1/10, because technically it's 1G divided by 10G. This equals theta, which equals 84 degrees. So you can see that the wider this angle theta is, then the more G force these people are experiencing. If you know V squared over R, you could also do Pythagorean theorem, but it's a lot easier just to use basic trig. All right, next page. Here's why I'm using acceleration for everything and I'm not using mass or force. Mass times acceleration equals force, so what I've done is just taken mass off of all of the legs of this triangle. So instead of mg force pushing down, mv squared over r pushing out, and ma, mass times acceleration, being the g force that those people feel, you can just drop the masses and just use the accelerations. And here's why: tan theta will equal opposite divided by adjacent. That's mv squared over r divided by mg. Mass divided by mass cancels. We're left with v squared over r divided by g, which is the same thing as v squared over rg. Same thing as cos theta, which is adjacent divided by hypotenuse. That'll be mg divided by ma. Masses cancel. You're left with g over a. Here's a nuance that's important to remember. I often forget this. When writing a complex fraction, make sure you draw your small division line as much smaller than your main division line, because I initially drew these about the same size. So they do have to be different, because v squared divided by the quantity r over g, then that puts g in the denominator of a denominator, which means you would multiply by g, and that's wrong. So I have my main division line here above the g, which shows that g is just in the denominator. Next page. Bonus trivia. From what I can tell, this is how you calculate the g-force on a swing at a playground. I made up these numbers because they're approximate. Feel free to use your own numbers. We'll say the radius of this chain right here is 4 meters, which is about 13 feet. We'll say that this person swinging on this swing going back and forth, they can get up to about 2.5 meters high, which is about 8 feet. Let's use the basic kinematics from physics, which is v final squared equals v initial squared plus 2ad. V initial squared will be 0, because we're going to say this person is starting at the top with 0 velocity in the y direction, and now they're going to swing down. Whether this person goes down on a swing, or whether they come down on a pole vault, or whether they just jump off of a wall and free fall vertical, their velocity will be the same when they get to the bottom. And this is ignoring air resistance. I did a video explaining this and showed some proofs, so you can see that video if you want to. It was labeled something like pole vaulting, I think, or radians and area under the curve. I think it was had those labels on it. At any rate, initial velocity is 0. We just have 2ad, so that's 2 times acceleration from gravity, 9.8 times 2.5 meters, because they're starting 2.5 meters high. So the v final velocity, 7 meters per second, which is about 16 miles per hour. Now we can find the centripetal force, or the centripetal acceleration, or centrifugal force, whatever you want to call it. That'll be v squared over r. I'm leaving off mass again, because when you calculate g-force, you're actually just calculating acceleration and comparing that to gravity. The fastest velocity that this person on the swing will experience will be when that swing is vertical, or the chain on that swing is vertical. So we take v squared, which is 7 squared, divide that by 4 meters, because that's the radius of the swing right here, or the radius of that chain, the length of the chain, I guess I could say. We get a centripetal or centrifugal acceleration of 12.25 meters per second squared. but this person is experiencing two accelerations. One is from the centripetal force, the other one is from gravity. So we add 12.25 to 9.8, take that total, divide by 9.8, and we get 2.25 Gs. So they are experiencing 2.25 Gs of force.